the WebEx will be recorded today, both the visual presentation as well as the audio over the telephone line. If for some reason you do not want to be recorded, feel free and send your comments through the WebEx chat, and we will try and get those over to Jordan.
Are they all gone now?
And please also mute your lines when you are not speaking. We do have a number of people calling in, and that way we will not have the background noise or the echoing. And with that, Jordan, I'll pass control over to you.
Yeah, great, thank you. I am starting the presentation now. All right, can somebody confirm that my screen is visible over the WebEx?
Confirming.
Sorry, Rebecca, was that confirmation?
Yes, Jordan, we can see your screen.
Great. Okay, so thanks everybody for coming. Let's talk a little bit about the development history of heRo, so specifically heRo3. So heRo3 has been under development at PAI for almost 3 years now, first in its previous incarnations as heRo1 and heRo2. In 2017, Merck, Amgen, and Novartis committed $375,000 in unrestricted funding to support the final phase of heRo3 development. However, those development partners have no interest or control over heRo3. And the heRo3 platform will be available for deployment and use by really anybody who would like to license it. Pilot testing of heRo3, heRo3's beta release, began in November 2017, and that's currently ongoing. And 150 plus analysts and modelers are currently participating in that process. Official launch of heRo3 is expected to occur in the second quarter of 2018. So a bit about heRo. We think of heRo as a new paradigm for doing health economics modeling. So heRo3 is a web-based platform for building cost-effectiveness models as interactive web applications, and that can either be done in the cloud or ultimately behind a corporate firewall. The calculations for heRo3 are performed in R, the open source.
Hello, this is Lilly Corporate. Mark Boy. Whoops.
Hello.
Hello.
Yep. We're in the middle of the presentation now, so we're going to continue with that, but we'll have time for questions later.
Mark, it's Jerry. If you'd be so kind as to just go on mute when you're not asking a question, that'd be great. We've got a lot of folks online.
So all calculations for heRo3 are performed in R, the open source programming language, and we have a special package that's been developed called heRoMod, which performs those calculations, and that is available on the web at the link shown, and you can look at the source code as well as the tests that are run on that package. So heRo3, the platform supports development and deployment of Markov cohort and partition survival models, though in the future we expect to add support for additional model types. So we've described heRo3 as a new paradigm. So I guess the question is, why do we need a new paradigm? What's the problem with the existing paradigm? And of course, the existing paradigm is building models in Excel. That's what we've been doing for more than 20 years now. And so, our process for building models in Excel has a number of flaws. I mean, typically, these models are developed on a bespoke basis. So anytime you have a new project, you build a model pretty much from scratch. There's not a whole lot of efficiency in that process. A lot of work is duplicated because of the way that process is typically done. It also means that because we're generally building models from scratch, a lot of the validation work needs to be done from the ground up every single time. And that really takes up a considerable amount of resources. And then finally, this existing paradigm results in some pretty steep training costs because every model is really its own piece of software that works rather differently from other models. And it gets worse when you look from, a product that's put together by one modeler versus another modeler, or from one shop versus another shop. There's not a whole lot of consistency. And so anytime you're working with a new model, it's an entirely new piece of software that you need to become comfortable with. So why is heRo3 different? We believe that heRo3 provides an enhanced level of transparency and robustness. The reason for that is that all of the calculations are done in this open source modeling package. And that means that the vast majority of the sort of programming work that is done for a model built using heRo3 is done using this common code base, which is tested and validated to ensure that it works properly. And that, that source code can be examined online, line by line. You can run a model with line by line debugging if necessary. And so we believe that's a level of transparency that our sort of current paradigm can't really match. An additional benefit is that there are significant programming efficiencies and cost savings. heRo3 has a lot of functionality built into it that makes developing certain kinds of functionality much simpler and much faster to do than in Excel. heRo3 also offers a structured framework for model building. In other words, we have a layer of formalism that sort of lays on top of your model. It's a formal set of steps that the modeler goes through. And what that does is it ensures that models are built using a common set of best practices, and that really there's a lot greater comparability between any two models built using heRo3 than any two models built using Excel. And so that makes them much more approachable. It's got engaging graphical, an engaging graphical interface and displays. The look and feel of heRo3 is built based off of Google Material Design, which is an increasingly popular design framework for web applications. The version control and lifecycle management is much improved compared to Excel because when this platform is fully launched, the models will be saved on the server and accessible via a URL. And what that means is if there's some change that you need to make to your model, if, for example, there's an error that you'd identified and you need to fix that error, making sure that everyone gets the new model is simply a matter of updating your model and saving it again. And that way, once anybody goes to access the model, you will know that they are accessing the most recent version of that model. In Excel, oftentimes the way the models are distributed is via email. And, to know everybody who's on the distribution list for that, you may send it to one person, they send it to someone else. And if the model needs to be updated, if there's an error that's found, and you want to send it out again, and that updated model might not make it its way out to everybody who has the old version, and that can lead to all kinds of problems. We also believe that heRo3 provides a deeper understanding of how models work because of the way it's set up. It provides very immediate and visual feedback. When you change a parameter, you can see the change of that parameter on any output. And see it in real time with nice, clear transitional animations It's a very different process from working with Excel. So a little bit more about heRo3. What heRo3 really is it's a secure platform and interface, user interface, for running open source modeling packages written in R. And so through our heRo3 user interface, you create cost-effectiveness models and you view the results. The calculations, as said previously, are performed on our server using the data that was received from the heRo3 front end, and those calculations are performed in open source modeling packages. And then those results get returned back to the heRo3 user interface where you can navigate them. And so even though all the calculations are done in R, heRo3 lets you build models in R without needing any sort of material programming experience in R. It reduces the process to something that is far more approachable, than writing an R script from scratch. heRo3 is also going to be mobile friendly, and that's going to allow you to ultimately deploy your robust CE models on tablet devices. So getting into the way the sort of models are defined in heRo3 and using the modeling package. We have a set of tables that define the structure of the model, and then within those tables, when user calculations need to be defined, they're defined as short R expressions, which are kind of the equivalent of Excel formulas. And in those formulas, there's a number of keywords and functions that can be used, which simplify the process of defining certain types of calculations in your models. And we'll get to specific examples of that functionality shortly, as well as at the end of this deck, when we send it out, you will see that there is a full glossary of functions and keywords that can be used. So getting into the steps for building a model in heRo3. So we've broken it down into an 8-step process that every model goes through, regardless of whether it's a Markov model or a partition survival model. So the first step is decision. In other words, what kind of decision needs to be made? What kind of comparison is being made between different strategies? We're going to skip over that one because that one is still in development. So the next step is settings. And on the settings page, we define relevant information like the time frame of the model, the cycle length, the country it's being run for, as well as the method that's used to handle half-cycle correction. The third step is groups. This is where we define the population of the model and which groups make up that population. So if a model is heterogeneous, then different subgroups can be defined, as well as the characteristics on which those subgroups differ. Next step is states. This is where we define the health states that go into the model. Step 5 is strategies. And so these are the different strategies that are being compared within the model. Step 6, transitions. And so that's where we define the probabilities of moving from each health state to each other health state. In a Markov model, this is defining a transition matrix. In a partition survival model, this is where you would define distributions of PFS and OS. Step 6 is values, and that's where we determine outcomes and costs that you care about with respect to state residency or transitions between states. And these are sort of individual line items and outcomes and costs that are being defined. And then step 8, the last step, summaries. This is where we aggregate those measures, the individual values, into categories of results that you want to display. Things like QALYs, life years, healthcare system costs, et cetera. So I think one thing you'll have noted about this process is that it's far more formalistic than anything like it, like in Excel. In Excel, you start with a totally blank workbook when you start building a model, whereas in heRo3, we have this, I guess you call it an opinionated framework for developing a model. We believe that this level of formalism can substantially improve the quality of models you develop and make them more understandable. So once you've got a little bit of experience with the heRo3 platform, you're going to know exactly how to look at a heRo3 model because they're all going to be laid out in a relatively similar and straightforward fashion. So with that, let's jump into a simple example model. We'll start with a Markov cohort model with 2 strategies, SOC/natural history, and then a new drug strategy. There's going to be 3 health states, well, sick, and dead. We're going to have a cycle length of 1 year and run it for 20 cycles. And we're going to produce outputs for costs, life years, QALYs, and the ICER, both in terms of dollars per QALY and dollars per life year. So I'm going to jump over to a live demo of heRo right now. So I'm going to open up the model. And here you can see we have the model open. Right along the top here are our 8 steps. And so we're currently in the decision step, which is currently disabled, so I'm going to skip past that. And now we're on the settings page. And so here you can see we've set the country to United States. We've set discount rates for outcomes and costs to 3%. We have an annual cycle for 20 years. And we're using the life table method for sort of dealing with the trace. And so, adjacent entries in the trace are going to be averaged when calculating our costs, life years, and QALYs. Going to the next screen, the group screen. This model doesn't have any heterogeneity defined. There's just a single group of patients, as is the case for the typical model. And so we did not have to define any groups. Now, if we wanted to define groups, we could just do so by clicking the Add Group button over here. Moving on to the states page. Here we defined states for well, sick, and dead. We've set initial probabilities here, so 100% of patients start in the well state, since that's the initial state. Moving on to the strategies page. Here we define our strategies, which are the natural history / SOC strategy, as well as the new treatment strategy. Next, we get to the transitions page. So on the transitions page, before I get too deep into this, I will note that at this point, we're starting to do some calculations. And so on this page, we're defining the transition matrix, but there are, of course, a lot of calculations that go into defining a transition matrix. And so before we sort of delve into this, I'm going to take a slight detour and take us to the variables page, which is over here on the sidebar. It's this little X icon. And so I'm going to go to the variables page. And this is where we would define inputs to our model, input variables to our model, as well as some basic intermediate calculations. And the way it works is that each row in this table is a variable that's being defined. So it's got a variable name, kind of like the range name in Excel if you made an input variable named range. There's a simple description for it, a category, and then over here there's a formula, which is just a short R expression, which will determine its value. And you can see all of these variables here are just input variables. They're just being defined as numeric constants, so those are inputs. And this one, for example, is the probability of getting sick for the natural history strategy. And so it's a probability of 0.5. There's also here the probability of getting sick for the other strategy, which is 0.3. And there are various other inputs defined here. Some of them are transition probabilities. Some of them are costs, so this is the cost of the new drug. Some are utilities or disutilities. And then at the bottom here, you can see we're doing some intermediate calculations. So this utility value for the well state for the new strategy is defined as the utility value for the well state for the natural history strategy minus the disutility associated with the well state for the new strategy. And any of these formulas, just I would note, you can click into them and edit them. And when you do that, they edit in the formula bar up here. And this is a sort of a structured, formatted text editor for working with your formulas. It's actually a lot like the Excel formula bar where there's contextual information provided. And if you start to reference a variable, suggestions will pop up, allowing you to more easily use those suggestions. So on this page, we defined all of our input variables as well as a few intermediate calculations. Now, going back to the transitions page, we can then define our transmission matrix by referencing those variables. And so the way this page is laid out is that there are columns for strategy, from state, to state, and formula. And so strategy, that actually, even before I get into that, this layout, we like to call it the long form format for transition matrix. And so instead of being defined as a matrix itself, each one of these rows represents an entry in your transition matrix, or in one of the two transition matrices, since we have two strategies. And so this first row, this is an entry in the transition matrix for the natural history strategy for going from the well state to the sick state. And the probability of that transition is defined by this formula, which is simply referencing the probability of getting sick for that strategy that we defined on the variables page. And then this next row, you can see this is for the new strategy, and it's also for the probability of going from well to sick. And it references the probability of getting sick for the new strategy that we defined on the variables page. So these two entries are in the equivalent spot in the transition matrix. It's just for one is for the natural history strategy, and the other is for the new strategy. Now the next entry, under strategy, it's marked as all, which it means that this same formula will be used for both strategies. And this is for the probability of going from the well state to the dead state. Now, dropping down to the next transition, this is the last transition from the well state. This one is defined for both strategies. So this is the probability of going from the well state back to the well state, so the probability of staying in the well state. Now, this probability is defined just as a single capital C, and that's a keyword. So what I mean by keyword is that this is a special variable that the modeling package will recognize. And what it stands for, in this case, what the capital C stands for, is the complement. And so this will automatically calculate 1 minus these other transition probabilities from the well states. And so now all the transitions from the well state for both strategies will sum up to 1, because this will take on the value of 1 minus the other probabilities. And down here you can see we've defined the other possible transitions from sick to dead, sick to sick, and then dead to dead. And so that covers our transition matrix for both strategies. Moving on to the values page. So on the values page, we define two different types of values: health values and economic values. And so you can see we've got two pairs of two tabs here that control each of these. So we're going to start in the health values page. And on the health values page, each one of these row groups here, which I can expand, is a line item in results. And so this first one, well life years, represents the life years that are going to accrue while patients are in the well state. And so when I expand this, when I expand well life years, what we get under that is a set of entries which correspond to the different ways well life years can accrue. And so within that, there's strategies. So this is the strategy column here. Apologies, it's being cut off on the screen. And so you can see that this is set to all, meaning that this row, defining a way that well life years accrues, applies to both strategies. And then there's the state column here, which represents the fact that the well life years only accrue during the within the well state. And the amount they accrue by in the formula column is defined by the cycle length in years. Since this is a per cycle quantity, the amount of life years that you get for being in the well state is, of course, equivalent to the cycle length. And so the formula here just defines how much well life years is being accrued per cycle that they're in the well state. And then similarly, we define sick life years, which is just the same thing except in the sick state. Then below that, we defined well qualies. And to do that, we're first doing it separately by strategy now, since they have different utility values in the well state. And then we're taking the utility value for the this strategy, the natural history strategy, and we're multiplying it by the well life years. And so whatever well life years accrue, we just multiply that by the utility value, and that gets us our well qualies. And similarly for the new strategy, we're just doing the same thing, but multiplying it by the well utility value. The well utility value for the new strategy. And then sick qualities is defined similarly, and so like that, we've defined all of our different line items in life years and qualities. Moving on to economic values, this is where we would define primarily costs, and so we've defined a couple of those. We have an item for medication costs, and this is something that only applies to the new strategy because we're assuming that the SOC strategy doesn't have a medication. And so we define the strategy as new. We define the state as well because we're assuming in this case that they are on therapy only during the well state. And then in the formula here, this is the cost per cycle of the new drug. And then below that, we have an item for terminal care cost. And so what we've done here is under state, instead of selecting one of the individual health states, we can select a transition between health states. So here we're selecting the transition from sick to dead. And so any patient who transitions from sick to dead will get this terminal care cost, which is defined as the cost of a hospice stay, which we defined on the variables page. So moving on to the summaries page, the last step. And here we define for both health summaries and economic summaries how we aggregate those quantities that we defined. And so, for example, here we've defined a summary called life years, which is made up of well life years and sick life years. So life years, quite simply, equals the sum of well life years and sick life years. And we've defined a willingness to pay for life years of $100,000 per life year. And so that will define life years as a valid denominator in our cost effectiveness analyses, as well as an outcome that can be looked at separately. And similarly, we define qualities here with a willingness to pay of $150,000 per quality, and we've got well qualities and 6 qualities making that up. Economic summaries work the same way. We defined healthcare system costs. We, of course, don't need a willingness to pay for economic summaries, and that's defined as the sum of medication costs and terminal care costs. So that is a simple Markov model in heRo3. At this point, I'd just like to quickly stop for questions, and then after that, we will look very quickly at a similar partition survival model, and then move on to some more advanced functionality. So now is the time. If you'd like to ask a question, please just speak up.
Can you hear me?
Sorry, go ahead.
Can you hear me? Can you hear me? Yes.
Yeah.
This is just a general question. So in terms of your modeling approach being used, has it mainly been used in the US? Is it more, can you sort of give me some applications? So what I'm thinking about is if you were to use this, say, in a market where you have to submit to an HTA body, do you know of any examples where this has been used, or has this generally been applied for US context?
Just as a note, there have been some models that have been submitted to NICE, I believe, using R, just actual, fully scripted models developed using R, and I do believe they will accept them. There has not been an HTA submission based on the heRo3 platform specifically yet. However, we are, reaching out to HTA agencies to, of course, bring them on board. And this is something that, ultimately I think could be the basis of HTA submissions. There are actually a lot of benefits to offering a model like this to an HTA, because from the HTA's perspective, there's a lot greater uniformity in models built using a platform like this than in Excel. And potentially it could save them really considerable amounts of time in, digesting a model that's provided by a vendor, understanding its structure, and then being able to quickly modify it and change assumptions and to view the results quickly. So we believe ultimately there are a lot of benefits to HTAs for accepting a model like this, and something we will hopefully see in the future.
Actually, there's also benefits of having some standardization within a company for when you do adaptations for local countries, because it's much easier for the local offices, the people there, to know what to expect coming their way, and when they get into the model, they know where things are and where to find them. So it does have some wider advantages, actually.
Yeah, absolutely.
Yeah, Mark Chapman from the UK as well. A couple of questions. One is, have you had the model outputs validated against the raw R programming and a comparable Excel build? And has that comparison been published?
We have done the validation. It has not been published exactly. Well, the R package that this model is that this platform is based off of, there has been some stuff that's been published on the web. I don't know if it's been published on a journal yet. Explaining the software and confirming that it's been validated. Yeah. The package itself, both the original version and the modified version that we use for this platform, is also available in sort of full source code on the web, and it's possible to quite easily download it and run the test set on it and confirm that the R package itself yields the correct results. And then in addition to that, we run testing on our end on every release to confirm that the models that we produced continue to match an Excel model.
Okay, no, that's great, and I think it's a fantastic tool. But I think when we look at HTA, and you mentioned NICE there, then the lack of peer review comparative outputs and its uniqueness would probably lend itself to be some way off being accepted as a template, which is something to aim for, really. The second thing is, it is a paradigm shift in putting a bit of simplicity around some of those things that we probably all had sleepless nights at university on. But there are other competing software packages looking to achieve this. So how do we think heRo differs from some of the other models in the marketplace? Because we could get competing outputs, which leads HTAs back to just the raw input R and Excel. Just wondered if you thought about that.
Well, most of the competitors that we've seen replicate part of what we're doing, but not really the whole package. Just as an example, there are some other modeling package that I think, bundling packages that are development in R, but I don't believe any of them offer this sort of full service web-based interface that's really ready for, you know, a sort of an enterprise level use case.
Okay.
By contrast, there are some other web apps that are sort of enterprise ready for building models, but they're not really web apps for building models. They're like one model that somebody has built and is offering use for. So they don't really have the scope in terms of what can be developed. And so we so far like to think that we're unique in the space of offering the full sort of spectrum of that functionality.
Okay, no, that's fair. Okay. No, thank you. They're my questions. Thanks.
This is Adnan. I have one question for you. So in heRo3, it seems to be it's kind of closed system. I cannot add my own functionality from R to heRo3. Example. For example, if I don't want to fix cycle length and I want to variable cycle length, for example, first cycle length in the model should be 6 months. After that, it's starting being 1 year. And in R, it's easy, you could do that. Anyone can bring his own codes from R and implement it to heRo3 to enhance in heRo3 for specific modeling project?
Sure, so that's a great question. And the answer is yes, depending upon exactly what you're doing with that code. So the specific example that you've raised of modifying it to allow for a variable cycle length, that's not currently supported. However, the model builder here does ship with a code editor over here, and I'm just going to go to that right now. And this is an area where you can define a set of R scripts that are going to be run. And so I'm just going to add an example on here. And in here, you can write any sort of R code that you want that's going to be run prior to the execution of the model. I'm sorry, someone's getting a lot of noise on their end. If they could be sure to mute their line. Great. So any code that you want to write into the, any R files that you define here is going to be run prior to executing the model. And what that's going to allow you to do is to do things like estimation. So you can write code here that's going to estimate inputs to a model and then reference those. You can also define functions that you can call within the formulas of your model. And so if there are, operations that you want to, standardize and perform, and you can put them in these R files and then call them from within your model. And so that does allow for a lot of expansion of functionality. It just doesn't quite allow for something quite as fundamental as the example that you provided. But of course, if there's things that you'd like the platform to do that it doesn't currently do, we welcome feedback, and we're always looking for ways to improve it. And so variable cycle length, I think, is certainly one that people will be interested. Okay, so at this point, I'm going to move on to doing a demo of a partition survival model. So I am going to open one of those up. And so in a partition survival model, I would just note really that there's not a whole lot that's different. So one of the nice things about this platform is that the process of going through developing a Markov model is almost identical to that for developing a partition survival model. So for example, we go to the settings page. It's going to be the exact same information. The groups page is the exact same information. The states page currently is slightly different. Right now, we're limited to three-state partition survival models, though that's a something that we're going to restriction we're going to relax in the near future. So there's just sort of 3 states: progression-free, post-progression, and dead, and you can rename these states, but sort of still need a sort of an equivalent progression-free, post-progression, and dead states. Strategies page is the same. Now on the transitions page, this is a little bit different. Instead of defining a transition matrix, you're defining distributions of PFS and OS for both strategies, or for the set of strategies that you defined. And then there's a formula here that will represent the survival distribution for PFS and for OS, and we're just referencing those. And those are defined on the variables page. And we have a separate section in the variables page called survival distributions, which is where we define those distributions. And so you can see here, just going to open up this formula. For this strategy, for this survival distribution, PFS chemo, we're using a function define survival, which is used for defining a parametric survival distribution with a given parametric form and a given set of parameters. So here we're saying that this is a Weibull distribution with the given shape and scale parameters, and that's going to define our Weibull distribution for PFS chemo. Then for PFS targets, we are using a different function, apply HR, which applies a hazard ratio to an existing survival distribution. And then we pass in PFS chemo, the Weibull distribution that we just defined, as well as the hazard ratio that's being applied to it, which is defined on the parameters page. And that gives us a proportional hazards model where that previous Weibull distribution has a hazard ratio applied to it, and that defines PFS targets. And then we do something similar here for OS, where for this chemotherapy strategy, we're defining an OS distribution according to Weibull. And then for the other strategy, targeted therapy, we're taking that OS curve and applying a hazard ratio to it. And so with those survival distributions defined, we simply reference them on this page. So for PFS, for chemotherapy, we reference PFS chemo, and so on. And beyond that, everything else is the same. So the values page is the same. We define our life years and qualities and whatever other health values we want to define. We define some economic values, some health and economic summaries. And so really all that's changing is that you are working with 3 specific states as opposed to a custom set of states, and you define distributions of PFS and OS rather than a transition matrix. So any quick questions?
Yeah.
Yeah, go ahead.
So what if you had your Kaplan-Meier survival curve from your clinical trial that you wanted to put into the model? How would you do that?
Sure. So this is slightly skipping ahead, so I'll just run through that now. No, that's okay. We can run through that now.
No, do it. Well, I don't mind. Just do it in the order that you. It's fine.
That's fine then. Okay, so we'll cover that in a bit.
Okay.
Any questions specifically though about the sort of model we've seen so far, the partition survival model? Bearing in mind that we will go over some more complex cases with how to define survival distribution. Okay, we'll jump ahead to results then. So what I'm going to do is I'm going to show you base case results, which are in this ref screen over here. And so this is the base case results page. You can see there's a bunch of different categories for results at the top. So there's our model trace, outcomes, costs, net monetary benefits, and cost effectiveness. And so for trace, what we're looking at is a trace chart here, which shows the probability of being in each state over time. And so this is currently displayed as a line chart. However, for each of these output options, there's a number of different visualization options that can be selected. So we can switch if we want from a line chart to an area chart, and it will morph into a stacked area chart. If we want to look at a tabular display, we can also do that. And then we get a nice tabular display showing the probabilities of being in each of those states for each model site. Now, on the right-hand side, you'll see there's a set of options which can be used to control this visualization. So if we, for example, want to look at targeted therapy instead of chemotherapy, we can simply just select that here, and we can see the chart changes. So you can see OS is higher for targeted therapy than it is for chemotherapy. Over here, we also have a set of user override values that can be sort of pinned up here. And so we've pinned a particular parameter here, which is the OS hazard ratio for targeted therapy. And so this will control OS for targeted therapy. And we've pinned this so that we can change the value and quickly see what the results are. So what we're going to do is we're going to make targeted therapy more effective in terms of OS, and we're going to rerun the model. And you'll see that the OS curve goes up as expected. So I'm just going to do that one more time. Increase the effectiveness of targeted therapy, have it recalculate, and then the curve will move up with a nice smooth animation. Now, it may not look smooth on your end because of the WebEx, of course, but it's nice and smooth on my end. Now, moving to the outcomes page. Here we show the health outcomes that are defined. These are essentially health summaries. And within each health summary, it shows the breakdown of the different health values that make that up. So this is currently showing a bar chart for life years. So you can see we've got our progression-free life years, our post-progression life years, and the total, both for chemotherapy and for targeted therapy. Now, as with the trace, there are a number of different ways we can visualize this. So we can move it to a waterfall chart and show how the individual components add up to the total. Or we can look at a tabular display. So we can see chemotherapy, targeted, and the difference. Now, we also have a number of different configuration options over here. There's a sort order, which you can change, which I won't get into here because there's only 2 items. Over here, we can choose the outcome. So instead of looking at life years, we can switch it to QALYs. And there we see the QALYs. We can change it from discounted to undiscounted if we want to look at the undiscounted values. If we only want to look at, say, targeted therapy, we can uncheck chemotherapy down here, and we just get QALYs for targeted therapy. Or we can bring it back. If we want to look at differences, we just select difference over here. And now we have, chemotherapy versus targeted therapy. But of course, we can change the reference to be targeted therapy, and then it'll show us the other way around for targeted versus chemotherapy. And of course, we still have our override values down here, so if we want to change that OS hazard ratio again and see what the result is, hit a calculate, and then you'll see the chart change. Next, we have the cost page, which has really the same set of graphing options as the outcomes page, except now we're looking at items of cost. So, again, we can do a waterfall chart. We can do tabular output. And, of course, we can change any of the other options previously seen. Next, we have net monetary benefits. And this will take all of our, first we define a health outcome that we want to use. So in this case, it's life years. And we define an economic outcome. And for the health outcome, it will take all the values that are part of that health outcome, that part of that health summary, and it will monetize them according to the willingness to pay threshold that's defined for that summary. And then put those on the same axis as the costs. And so you can see here, we're looking at net monetary benefit for targeted versus chemo based off of life years and healthcare system costs. And for targeted therapy, there's a gain in progression-free life years, and so that adds a certain amount of monetary value. There's a gain in post-progression life years, which adds a certain amount of monetary value. And then there's a bunch of monetary value lost because it increased medication costs, as well as slightly increased progression-free and post-progression care costs. And the total net monetary benefit is negative, meaning that it's not cost-effective at the willingness to pay that's currently set. Now we can switch this over to life years if we want and see what the NNMB looks like for life years. We can also change the sort order. So for this one, I like to sort it numerically so we can just get a sense of the biggest value losers versus the biggest value gainers. So you can see the biggest drag on the value of this project is the medication cost, where the biggest value added is the progression-free QALYs. And then, of course, we can do things like change the reference or change the override value and see how that affects the results. Just an additional note here, at any time, if you feel like you want to get a larger, sort of bigger view of this figure, you can simply hide this options panel and you'll get a full screen view. And then finally, for the base case results, we have the cost effectiveness page. So here it shows the cost effectiveness frontier. And so you can see chemo and targeted therapy are both on the frontier. this frontier is actually animated, and so if we set the OS hazard ratio here to 1.1, we're probably going to make targeted therapy dominated. And so what you'll see here is that this marker for targeted therapy is probably going to move to the left, signifying that the effectiveness is decreasing, though also probably down a bit, signifying that the cost is decreasing. And when it passes chemotherapy here, it's going to pop off the frontier, and the only thing on the frontier will be chemotherapy. So I'm just going to rerun this, and it's going to move down, and you can see it's now off the frontier because it is dominated by chemotherapy. Now we also have a tabular view for the cost effectiveness, and you can see here we've got our life years, our costs, the costs for the healthcare system. Oops, apologies, this is out of order a bit, but we've got chemotherapy and targeted therapy, and chemotherapy dominates targeted therapy. So in this case, the ICER is displayed as negative. So that's base case results. Moving on quickly to value-based pricing. Every heRo3 model comes with a VBP calculator. And so what this will show is, once you've configured the options on the right-hand side in terms of what health outcome and what economic outcome you're using. So in this case, we're going to calculate a VBP that's based off of a healthcare system cost per QALYs setup. We're doing this from the perspective of targeted therapy. And so in other words, the price that we're calculating is the price of targeted therapy. We also need to specify the price parameter. So this case, the price parameter for target is this variable that we would define target costs, as well as the maximum willingness to pay that we want to show this for. And I'm just going to get rid of this override value that we set before and have it recalculate. And what it's going to show in this chart is it's going to show the relationship between the price of the drug, in other words, the value of target costs, in relation to the willingness to pay that is achieved. So for example, at a willingness to pay of 50,000, if we want to be cost effective at that WTP, we need the price that's about a little above 2,000. If we want the exact values, we can of course go to the tabular view. And so if we want, for example, the willingness to pay at 60,000, this is the exact value that needs to be set for the price of targeted therapy. And so very quickly, we can set up a VBP analysis for any model that we developed. And this VBP calculator is set up to work even if you have multiple strategies that you are comparing against. It will calculate your VBP against every other strategy as well as the minimum of those, which will make you cost effective against all strategies. And then after VBP, we have our DSA analysis. And so in this DSA analysis, we've defined on another page a set of parameters that we're varying them, as well as the range over which we're varying them. And we have tornado plots for outcomes, for costs, and just you'll note here, in the outcomes tornado plot, there's only 2 entries, and that's because of the things that we're varying, only 2 of them actually affect life years. And so this will automatically pull out any parameters which have no effect on the output of interest. But anyway, we have various tornado plots for costs, NMP. We don't have a tornado plot for CE. We just have a simpler tabular output, since tornado output for ICERs is not always well defined. But we have tornado plots for all these other outcomes. Now, we're running a little bit behind here, so I want to quickly move on past results. But are there any quick questions about the results displays? Okay, moving on. So now that we've covered a basic case, we're just going to go over a few sort of general sort of pieces of information about the platform that we haven't covered, as well as a few sort of tips and tricks and more advanced functionality that wasn't covered in our existing walkthrough. So the first thing I want to talk about is first-time use. So right now, I would just note that we are still doing the pilot testing, so there's some functionality that's not yet enabled. Going back to results, for example, the PSA functionality is not currently enabled, so we didn't cover that, though that will be provisioned at the time of launch. Another piece of functionality that's not currently provisioned is server-side saving of your models. So right now, the way models are saved is that they're saved locally on your computer. And essentially, they're saved within a special cache area of your browser. And that means that if you access the model from a different device, you're not going to see the models that you've saved previously. Now, don't worry, that's not a bug or anything. Your models haven't disappeared. If you just want to transfer a model that you've created from another device, it's possible to export your model as a file and then just sort of email it to yourself or take that with you, or if you want to share it with someone else, you can email that file to someone else, and then that file can be imported back onto the platform. But in the final sort of release of heRo3, of course, your models will be saved primarily on the server. That way, regardless of which device you access your model from, all of your models will be available to you. Now, one additional aspect of first-time use is that the first time you load up this application, you're going to see a screen like this, and you're going to see two things. First, actually, just another note here that I neglected. Currently, Chrome is the only browser that's supported for the platform. That's because of the storage method that we use for saving these models in your local sort of browser area only works on the Chrome browser. We're going to relax that restriction once we have server-side saving. But for the moment, we do ask that you use Chrome. We understand this is a minor inconvenience, but we just want to make sure that you have sort of a working user experience. And so with that said, when you first load the application, what the browser is going to do in the top left here is it's going to ask you for permission to store files on your computer. And you will need to hit allow here on that dialog. Because if you hit block, then the rest of the model functionality is not going to work. You're not going to be able to save any models. So please hit allow. And you're also going to be shown an end-user license agreement screen, and all you need to do is go through this and hit I agree, and then you will be allowed to use the platform. So once you get through the welcome screen, you're going to have some icons for opening existing models. You're going to have an area of the screen where it shows all the existing models that you've saved, and you just click on any one of those to open them. If you want to start a new model, there's some buttons at the top for creating a new Markov cohort model or a new partition survival model. And so you just click the kind of model you want to open or you want to rather create. Also, we have a number of predefined templates which exemplify certain kinds of model structures or certain types of functionality. And if you want to work with those, you can just go into the template panel and open any one of those. And just to quickly go back to heRo to show you that. This is the modeler workspace screen, as we call it. And so as you can see here, we've got buttons for creating a new Markov cohort model, a new partition survival model. This is the area where your models are defined. So if you want to open any of these, you just click on them. If you want to delete them, you click on the X, and it will prompt you as to whether you want to delete them. And then down below that, we have a number of predefined templates which will be available to all users, which exemplify, as I said, certain types of functionality. Just one more thing I'd like to note here, this little question mark at the top. This will take you to a help page which has all kinds of useful information about the platform. It will explain in greater detail what's happening on each one of those screens, as well as provide a complete listing of the functions and keywords that can be used within the heRo platform. So moving on to backing models up. So as I noted, currently the application is storing your models locally in the Chrome cache. Now, this is temporary storage only. There are some things that will happen that will clear that storage area. And so just to be sure that you don't lose any kind of important data, it's important to regularly back up any models that you've created. And to do that, you can use the export functionality built into heRo3. And so I will just quickly demo that. And so let's say we have opened up a model here and we want to export it. If you go to the top right hand side here of the screen, you can see there's a few different options. There's this undo and redo buttons here. There's the folder button here, which will take you to the model or workspace screen. There's a save button here, which will just simply save your existing model, save over it. And then there's a save as button here. If you click that, and you enter a new file name and author and description for the model, you can hit export here, and what that will do is we'll simply download a file that represents your model, which you can then load back into the platform. And so that will ensure that the model is stored somewhere permanently on your hard disk, and you will know where to find it. Now, once you've downloaded it, once you've exported it, you can go back to the model or workspace, and if you need to load that model up again from where you backed it up, you just hit import model, and then you browse to where that model is and load it up. So that's how you export models. So exporting. So there's actually some more advanced exporting functionality that's also possible. So we've covered one type of exporting your model, which we call exporting to JSON, because JSON is the name of the file format that it goes to. But essentially, that's a transfer format for the model. It's a way to download the entire model as a file in a way that can be uploaded back onto the platform to reopen your model in heRo. And so you can use that both to back up your files as well as to send to someone else. There are other ways, however, to export your model. So one way is you can export it to R. And so just to demo that briefly. So over here we have a separate export page which allows for other type of export options. And so I'm just going to go to it over here, this icon in the sidebar. And so there are three different options here: export to R, export to Excel, and export to JSON. We already covered export to JSON. That's the same functionality as we showed up in the Save As screen. Export to R is going to download your entire model as a zip file that contains an RStudio project. And when we do this, it's going to allow us to open up the model and run it directly in R. So I'm just going to open this up, and open up the RStudio project in RStudio. And so now we have a project open in R. And I'm just going to open up this R file within that project. And there's just a little bit of simple code here that's going to install the necessary packages if you don't have those already. It's going to load in the data for the model, and then it's going to do this one function call that will run the model. So if I just run this, so it's running the results right now, and the results have been run. Now, doing it this way, you can also actually see exactly what errors are occurring when you run the model. You can run it with line-by-line debugging to see exactly where errors occur if you really want to go in depth with it. But this allows you to run a model offline and see those results without necessarily having to be connected to the heRo3 platform.
If you allow me, I would like to ask you, since you're talking about exporting to R, so I only can run the model in R. There is a way if I can share the entire codes of the model to a journal, for example, in the appendix. Can I do that?
Yeah, sure. Well, actually, in this case, it would. I mean, there are different ways you might want to display it. So, of course, you can put together a table with the same information as is displayed in the heRo3 application. You could also upload this zip file, which has all the information necessary to run it in R. But the representation of your heRo3 model is actually going to be rather simple. I mean, the whole thing is something, the set of tables that are involved could fit into a sort of typical supplementary materials page in a, in a journal, an online journal, for example. If the real bulk of the code behind the model is, of course, in our open source modeling package, which is already available on the web. If someone wants to go through the individual lines of code, they can do that online. But again, your model can be represented both just directly as a table. If you want to have that in a PDF document, you can put that same information in a PDF document, or if you wanted to, include this information that's exported to R, you can certainly do that. Really, the bulk of the model is in this RDS file.
So what I understood can I see the entire script of the R codes specified to my model itself? I understand you said about the package, it's out there and anyone can see it, but can I see the entire, codes for my specified model?
Jordan, did we lose you?
Sorry, I was on mute. Yes. If you want to sort of have a more tabular representation of your model with all these sort of different formulas that are involved, you can export it to Excel. And what this will do is it will show all of the input tables. So apologies, I'm opening this up now. So it will show all the input tables. So for example, this is the decision page. This is the settings page. Let me zoom in a bit. So we've got our discount rates, our strategies. Just skipping ahead here a little bit. This is the transitions page. So here's all the code for the different transitions. The parameters page here. And so these tables have the code that represents the model, and these could be put into, a supplementary, appendix kind of page. But I mean, really, it's important to note that there is nothing to your model other than these tables of information that you've created in the editor, as well as the open source R package. There's no real code other than that. I mean, the only code other than that is this one line, which takes the model information and then runs the model. Is that clear enough, or do you have any additional questions about that?
Yeah, that's clear. Thanks.
Okay, so those are the two additional export options. You can export to R and export to Excel, and we've already covered exporting to JSON. Actually, just one more thing about the export to Excel. In addition to exporting the inputs, this will also export all the results and calculated values. For example, you can see here that the trace results are exported. So this shows for each model cycle, for each strategy, the probability of being in the different states at full precision. It also shows the calculated values of all these parameters over time, all the different parameters that you've defined. It shows the calculation of the transition matrix for each cycle. So basically all of the internal calculations, all the results of the internal calculations are in here for you to look at if you want to examine them. So moving on, undo, redo functionality. We already showed where that is. It's in the top control bar of the application. If you make an error, you can use undo to roll back your model to its previous state. And you can go back as far as 10 previous actions. And redo will let you undo undoing. It will let you restore the actions that you eliminated with undo. So we do have undo, redo functionality built into the platform. So now moving on to a few tips and tricks and other hopefully useful advice. Time dependency is, of course, an important part of building Markov models. And so I'd like to discuss two different types of time dependency that can be very easily implemented in heRo3. So just as an example, we will go back to the Markov model that we were working with earlier. But instead of, we're going to take the transition from the well state to the dead state. And instead of using a constant probability, what we're going to do is we're going to make it so that it depends on a patient's current age using a life table. And so over time in the model, we're going to track the age of the patient, and the mortality rate will depend on their age using a life table. And so the way we're going to do this is we're going to define a table in the heRo3, which we haven't actually covered yet, but we'll show an example of this now, where we have put in a life table, some life table data, and then we're going to define a variable which represents the starting age, and then we're going to define another variable which represents the current age in the model, which is just the starting age plus the number of years that have elapsed in the model so far. And then we're finally going to define a variable which looks up the current mortality rate based on the patient's current age and based on that life table. So getting started on that, I'm going to open up the model for this and go to the variables page and just go over a couple additional things that have been added. So first, we've added a variable here for the starting age for the patient. And so we're assuming that patient starts at age 45. And so that's fine. We've also, in the tables page, which we haven't covered yet, we've defined a table here called life table, which we can reference in our formulas. And this has, the age of the patient, the probability of death for a male patient, as well as the probability of death for a female patient. And so what we're going to do is we're going to set up the lookup for those so that it pulls the appropriate mortality rate. So we're going to do that on the transitions page. And so in this transition for both strategies, going from well to dead, we're going to put our formula. And so we're going to use the lookup function, which is a lot like VLOOKUP in Excel, where we're going to be looking up on that table that we've defined. The first argument to look up is the table that we're going to look up on, which is called life table. And then next we're going to define the column that we're looking up on. And so that's the age column. So you can see here it's age equals, and then the value of the age that we're going to be looking up. And so what we're going to do here is we're going to take the starting age, which we defined on the previous page, which is 45 years old. And then we're going to add to that model year, which is a keyword which will take on the value of the current year it is in the model. So for example, in year 1, model year will be 1. In year 2, model year will be 2, and so on. And so start age plus model year will yield the current age of the patient in any given model cycle. And so we're just looking up in this life table the age that corresponds to the patient's current year, the age that corresponds to the patient's current age. And then the value column that we're looking up, so this value equals argument, we're looking up the column P death male, which is the probability of death for a male patient, because we're, in this case, just assuming that patients are male. And so we're looking up on that column. And finally, there's this additional argument, bin equals true. And this just allows for range lookups. If you recall in Excel, the VLOOKUP function allows for inexact matching. And so if you have a value, for example, of, if it's looking up year 1.2, and in the table there's only options for year 1 and year 2, then it will use the option for year 1. And so that's just making sure that if the cycles don't exactly align with integer number of years, that it will look up the appropriate value. So that's what this optional argument bin equals true does. If you set bin equals false or leave it blank, then it will look for an exact match. But anyway, this function will look up the appropriate mortality rate given the patient's current age in the model. And we've assigned this formula to be in this transition. And so now we have time-dependent mortality rates for patients. This is how we've introduced model time dependency. Simply by having a formula here that references model year, we introduce model time dependency, and this formula around it will ensure that the appropriate value of the mortality rate gets calculated as a function of the model year. Now, just to give a quick explanation on how this actually works behind the scenes. So, let's do just a quick diagram here which sort of covers it. So this table represents the transition matrix that we entered into the heRo3 platform. We've got our columns for strategy, for from, for to, and then the formula. And so the first thing we're going to do is we're going to take that formula column and we're going to expand it into two transition matrices. One for the natural history strategy and another for the new drug strategy. And so the way that works is just we're sort of taking whatever cells are defined by these entries and we're placing them in the appropriate transition matrices. And the items that are specified for all will go in both transition matrices. And then these two bolded entries, those are sort of strategy specific. And so the appropriate entries from each strategy go into the appropriate matrix. And so nothing interesting is happening here. We're just going from long form to matrix form. Now the next step, we're taking these matrix form entries, and we're going to deal with the fact that there's a reference to model year. So the platform is going to reference the fact that you've referenced model time, in this case, model year. There's actually other different variables for model day, model week, model month, model year, and all of which will sort of yield the appropriate time of the model at any given cycle in that unit of time. And so if here detects any reference to model time, what it's going to do is it's going to, for each cycle, substitute in the appropriate value of the model year. And so you can see here, instead of having one transition matrix, what we're going to get is actually one transition matrix for the first cycle with the appropriate value of model year substituted in, another matrix for the second cycle, another matrix for the third cycle, and so on. And so that formula gets evaluated separately, it gets evaluated to a different value in each cycle based off of, however the formula evaluates when you substitute in the appropriate value of model year. And so just like that, we've sort of done through the work of creating multiple transition matrices, one for each cycle, in a way that depends, that those transition probabilities will depend appropriately on model time. So any quick questions about model time dependency here, or the tables page, or using the lookup function? Okay, moving on to state time dependency. State time dependency, another type of type dependency, but this one, state time dependency, is dependent on not how long it's been since the model has started, but how long a patient has been in their particular state. So, you can have a transition probability, for example, depend on how long you've been in the sick state. And so the way this is handled is with tunnel states, but the heRo3 platform does not require that you explicitly create those tunnel states. Instead, they're created automatically, similar to the way that model time functionality is handled. And so we're going to go through another example here, except in this case, we're going to take the model that we just worked with, and then we're going to add some additional complexity to it, where the probability of going from the sick state to the dead state, instead of being a constant, will depend on how long patients have been sick. And we're going to do that using a Weibull distribution, which will determine, what the time is from, becoming sick to dying. So, going back to the heRo3 platform, I'm going to load up the next example model, which has this set up. And I'm going to go to the variables page. And so I'm going to scroll down here, and you can see we've defined a couple additional parameters. We've defined a shape parameter and a scale parameter. And these are simply going to be the parameters of the Weibull distribution that we're going to use to model the time from becoming sick to dying. So next we're going to go to the transitions page, and we're going to look up the probability of going from sick to dead. We're just going to open up that formula. Okay, so this formula is a little bit more complicated, so let me break it down from the inside out. So this is a couple nested function calls. So first I'm going to tackle this function call right here. This is actually something that we saw a little bit earlier in our partition survival model example, where we're using the define survival function to define a Weibull distribution using a given set of shape and scale parameters. So we're just defining that the distribution is Weibull. This is our shape parameter, this is our scale parameter. So this inner function call defines a Weibull distribution. Now this outer function call, this is the event probability function. What it does is it takes a survival distribution and it generates the probability of an event over a specified set of intervals. And what we're going to do is that we're going to use that to calculate our transition probabilities, because really the survival distribution, the probability of having an event during a particular interval, the conditional probability of having an event during a particular interval, that represents our probability of going from sick to dead. And so in order to generate these transition probabilities, we're going to take the survival distribution and use that to calculate the event probabilities in each cycle. And so the way that works is we're using the event probability function. The first argument is our survival distribution that we're defining. Then we have this argument start, where we're defining the time that represents the start of each cycle. And that has to be in the time scale that's used in the survival distribution. So this survival distribution, we're assuming these shape and scale parameters represent years, so we're passing in years here. And so for the start parameter, we're passing in a time that represents the start of each cycle, which is state year minus 1. And so state year represents in the first cycle, the value it's actually going to take on is 1. In the first sort of cycle that you're sick, the value is going to be 1. And so we're subtracting 1 here. And then the end is state year. And the value that we're using here is 1 because that's the cycle length. The cycle length is 1 year. And so essentially, this start thing in the first sick state, in the first cycle that patients are sick, this is going to take on a value of 0. And this is going to take on a value of 1. And so this whole function is going to calculate the probability that the conditional probability that a patient will die, given this Weibull distribution, between time 0 and time 1. And then in the second cycle, it'll be between time 1 and time 2, and so on. And so this will calculate our event probabilities, our transition probabilities from going from sick to dead. Now, to break down how this actually works in the platform, we'll do another one of those diagrams. Let me skip over that. Again, starting with the transition matrix. In this cell here, we have our reference to the sort of probability of going from sick to dead, which references state time. And so what the platform is going to do is it's going to detect that within the sick state, there is a reference to state time. And so that's automatically going to create a set of tunnel states within this transition matrix in order to reflect the fact that the probability of transitioning, from the sick state to the dead state will depend on how long you've been in the sick state. So now we have state sick 1, sick 2, all the way out to sick 20 in this transition matrix. And then the probabilities of going from sick to dead, so this set of probabilities over here, it's going to put in the appropriate values that are calculated for, state year minus 1 and then state year over here for the start and end. It will calculate these formulas with those values substituted in. So in sick 1, the first sick state, we're going to have a value of start equals 0 and end equals 1. And for sick 2, it's going to be start equals 1, end equals 2, and so on for each cycle. And that's how this transition matrix is going to be calculated. And then additionally, our probability of staying in the sick state, of going from sick to sick, that automatically, this formula here automatically gets put on the diagonal, or the slightly off diagonal part here. So the probability of going from, you can't go from SIC1 to stay in SIC1. Instead, if you stay in the SIC state, you go from SIC1 to SIC2, or SIC2 to SIC3, and so on. So any questions about state time dependency or using survival distributions to calculate these transition probabilities that we covered in this example?
Hi Jordan, this is Rituparna. I just wanted to know if there is a glossary or like a user manual where you have all these formulas in there, because it's pretty close to Excel, but there are like slight differences. I was just wondering if there is any like a user guide or user manual or a glossary.
Yes, I'm opening that right now.
Okay.
So, like, if you go to the top toolbar over here, you can see there's this help icon. So if you click that at any time, oops, we got a little problem there. We may have some temporary downtime on that user manual. But if you click that, it will take you to a user manual that has not only complete reference material on all the functions and keywords that you can reference, but also page-by-page descriptions on, what page each represents and what kind of information needs to be entered. In addition, we're going to distribute this deck afterwards, and there are other decks available online on the help material, which additionally have reference material on different functions and keywords that you can call.
Thank you.
Yeah, no problem. Any additional questions about state time dependency, or if you have a question about the previous example, model time dependency, now would be a good time for that.
Jordan, this is Jerry. Very quickly, the Atlassian just posted that they're updating their platform, and they'll be offline for 5 to 10 minutes, so that's why you couldn't access it.
Yeah, understood. Okay, moving on to the next item. So we've had a number of users, of course, on this platform now, and we've identified some of the areas which confusion occurs. And one item of confusion that we've noted is on the transition page. People are still getting comfortable with how to best set up transitions the way we've laid them out as a long-form table. And so I just want to go over some ways to make sure that your transition page can be kept nice and clean and understandable, and save you time, and make sure that you can set it up quickly and efficiently. So some various different tricks that we can cover. So first, in any given Markov model, usually there's a bunch of transitions that are simply not possible. In other words, the probability of undergoing that transition from state A to state B is always going to be 0. So when that happens, you don't even need to create an entry on the transition page for that transition. So for example, it's not possible, obviously, to go from the dead state to the sick state in the Markov model that we covered previously. And so when we look at that model, just going back to it, you'll see that there actually is no transition entered for going from dead to sick, because the probability is always 0. And so those transitions can simply be omitted. They do not need to be included in the transitions page. So the next item is filtering. And so this filtering functionality is available on a lot of pages, and allows you to just very quickly type into here a filter, and it will only show entries where that text is found in the table. So for example, let's say we only want to look at the transitions that involve the new strategy. I just type in new here, and only those entries will appear in our table. And that makes it nice and easy if you have a relatively long table, just to focus in on a set of entries. So the third item is that the keyword C is equal to the 1 minus the sum of all the other transition probabilities from that given state. We already showed an example of that, but just as another example here, we have the probability of going from sick to dead in this model. And of course, if you don't go from sick to dead, the other possibility is you can stay in the sick state. And because we don't want to calculate 1 minus this whole big formula here, we just type in capital C, and that will automatically calculate 1 minus the other probability. And so that can save a lot of time. And it also ensures that you calculate these complements properly. Sometimes people run into issues where they do not quite calculate the complement properly, and the transition probabilities don't quite sum to 1, and then that results in errors. And so error messages. Because, of course, it won't let you run a model if your transition probabilities don't sum to 1. But just to avoid that, using the complement operator makes it very nice and easy. Then item D, if the transition has the same value for each strategy, rather if it has the same formula for each strategy, select all in the dropdown and you can represent it as a single row. And so just as an example here, the probability of going from the well state to the dead state, that uses the same formula by strategy. And so we simply set that as all, and we only need to have 1 entry here as opposed to 1 for each strategy. And so that saves a lot of space when you have multiple strategies. Then item E is performing intermediate calculations on the variables page. So just an example of this, going back here, we have this relatively complicated formula for going from sick to dead. And this might be a little bit too much to digest on the transitions page. So what you can do is you can cut this formula. You can move it over to the variables page. So what we can do over here, so we can create another variable called pdef Weibel. And then we're just going to paste in that same formula. And then going back to the transitions page, we can reference pdef Weibel. And now we have a nice, relatively easy to understand variable name on this transitions page, and we don't have to digest the entire chain of calculations that led us to this variable. We simply have a variable here, which is we understand what it represents. And if we want to see the calculations, we can see that on the variables page. And then finally, sorry, go ahead.
If you allow me, just one question. I don't know if you already talked about it, but it's not clear to me when we have a transition probabilities for a specific state, just for the first 4 cycles, and after that should be 0. No one should go to that state, or maybe the reverse. Maybe at the 4th cycle, I'd like to move some patients to that healthy state. Only in that, only that, time, specific time.
Sure. So let's take the example here of this probability of death from the sick state. So let's say that beyond the 4th cycle in the sick state, the probability of dying is 100%. So you, for whatever reason, you can't survive more than 4 years, or that's really equivalent to not transitioning, but I'm just going to use that example here. So what we can do is we can use a conditional function to make that work. So we're still going to take this pdef Weibel because that's going to represent our probability of death during the first 4 cycles. But we're going to append to this the if-else function, which is kind of like an if statement in Excel. And so the first argument to if-else is the condition. So what we're going to do is we're going to do state year is less than or equal to 4. And so if we're in the first 4 years of being sick, then we'll use this value. And otherwise, we'll use a value of 0. And so like that, we have sort of made explicit sort of time-dependent logic and time-dependent conditional logic here, where we'll have one set of transition probabilities for the first cycle, one set of transition probabilities for the first 4 cycles defined here, and then another set there. Now, of course, you can do a similar condition where you use model year if you wanted that to be model time dependent.
And,
is that clear?
The same thing. Yeah, and the same thing. Instead of using a distribution, a Weibel distribution, I could use a table for the first 4 cycles, referring to a table. After that, should be 0. Is that correct?
Absolutely. You can define a lookup table and use the bin equals true argument. And, if you have 4 items in the table, one for cycle 1, cycle 2, cycle 3, cycle 4, the cycle 4 option will carry forward if you use the bin equals true argument. And if you're looking up, something from the 10th cycle, for example. I would also note, though, if you're using state time dependency and you want the last transition probability to carry forward in a formula, the most efficient way to do that is to go to the states page. And we have this item here, max number of tunnel states. What this is doing is it's essentially limiting the number of tunnel states to the specified amount. So just going back to our model time example, our state time example, when we created that state time dependency, it created 26 states, 1 for each cycle. Now, you may not want to do that if you have 200 cycles. Maybe you want to cap it at 10 tunnel states and have the transition probabilities for the last tunnel state carry forward. In which case, under the 6th state, you would set the max number of tunnels to 10. And then what it would do is it would cap it at 10. And so in the 10th state, if you're in state 610 and you are going back into the 6th state, instead of moving on to 611 with a different set of transition probabilities, you will stay in 610. And that's important because it's actually much more computationally efficient if you have a large number of cycles to limit the number of tunnel states. And so if you wanted to do that specifically, if you wanted a transition probability that cuts off after a certain number of cycles, you would also want to set the maximum number of tunnel states, just to ensure that you're not making our model take longer to calculate than it needs to. Okay, next item.
Last question. Last question.
Yep.
Can you specify, for example, Weibull distribution from a lookup table? Like you have for each row, can you do an arrays of, distribution specified for each row?
I'm not sure what you mean by that exactly. Could you just clarify that slightly?
Yeah, so I don't know. So there's no any BSA examples today. Is that correct?
I'm sorry. Could you repeat that? I didn't quite hear that one.
There is no any examples for probabilistic sensitivity analysis today. Do you have any?
No. So we're not currently the PSA functionality is not yet provisioned. That's something we're still working on. Yeah, so I was planning to ask you one question related to the BSA. If you can define for the tables you build, for lookup tables, if you can define the specific distribution for each row. But since you still is not. So, I mean, would the goal there to be to switch between different types of parametric distributions within the DSA?
Yeah, for example, if I specify the BMI change for each cycle, I would like to be resampled from a distribution for each cycle from the table itself.
Okay. Well, I mean, what you can do there, and I don't think you need multiple Weibull distributions necessarily. You would have you've got some kind of clinical variable which is feeding into the Weibull distribution and determining its parameters. Is that correct?
Now, for example, let's say about the normal distribution. I would like to resample the BMI change from the normal distribution for each cycle. So sometimes, since you're not going to cover the BSA, I think I'll ask you later when it's ready, the BSA.
Okay. Well, I think we've already covered the DSA. I thought you said PSA earlier. The DSA is provisioned. The PSA is not provisioned.
Yeah, the PSA, the probabilistic sensitivity analysis. So I'll ask you later when it's ready.
Okay, understood. So next we want to cover partition survival models and different ways to specify the survival distributions for those. So there are a few different ways to do that. So the first case is you have a Weibull function and you've already estimated the parameters for it. And we've actually already covered that case. That's just where you use define survival and you plug in the parameters for that distribution. And I would just note here that we've used Weibull a lot in the examples today. We have support for a really wide number of distributions. Just to name a few, we've got exponential, of course, Weibull, log logistic, log normal, Gompertz, generalized gamma, generalized F, various types of restricted cubic spline models, as well as mixture and non-mixture parametric Kerr models. All of those are set up so that you can define them. We're just using Weibull distribution as sort of an easy example here. And so if you have the parameters already defined, you simply use the define survival function, as well as a few other functions for defining more complicated types of models. And you tell it what type of distribution it is and what parameters are being passed in. Now, if you want to apply a hazard ratio to your fitted survival distribution, you can use the function apply_hr, and we already saw that in our simple partition survival model example where we used apply_hr. We passed in a Weibull model, and then we passed in the hazard ratio, and that yielded the Weibull with that hazard ratio applied. Now, another case that we can look at is working with Kaplan-Meier data. So let's say you have a set of survival probabilities generated from a Kaplan-Meier. So it's a set of times and a set of probabilities of survival. So what you can do is you can create a table in the tables page with columns for time and survival and paste in your survival data into that table. And then you can use the function define surv table with that table as the only argument. And that will create a survival distribution based on that table. And so it'll essentially automate the process of looking up the survival probabilities given the Kaplan-Meier output that you've put into it. And just to show an example of that, sorry, wrong model here. So I'm going to open up the tables page here. And here you can see we've created a table with columns for time and survival. And in the variables page, apologies, in the survival distributions part of the variables page, in this variable here called PFS_KM_chemo, we're using this define surv table function, and we're just passing in that table. And that's going to create a Kaplan-Meier distribution. And we're just going to quickly go to the results page so that we can see what that looks like. You can see that there's a Kaplan-Meier used here. Now, I would note here that it's actually not using the Kaplan-Meier for the entirety of the model. It's actually picking up with a parametric projection. So let's just take a quick look at how we set that part of it up. So we've defined one segment here with this variable PFS_KM_chemo. We also have another variable, which is, let's see here, where is it? PFS Weibull chemo. And there we're using the define survival function to do a Weibull distribution. And then finally we have the variable PFS chemo. And this is where we use the join function. And the join function allows you to stitch together multiple survival distributions at a specified set of times so that one will pick up where the other one left off. And so here we're joining the KM distribution to the Weibull distribution at time 20.1. And so you can see we've got the KM, and then we've got the Weibull, and those two joined together at this time here, which I believe is 20.1 months. And you can join any number of curves together. You can actually join 3 or more curves together if you want to do some very advanced survival modeling. We also have a number of other operations available for working with survival distributions. For example, we have a mix function, which allows you to mix 2 survival distributions together with the specified probabilities. We have a function called add hazards, which allows you to combine 2 survival distributions together as independent risks. So for example, if you wanted to add general population mortality on top of a survival distribution, you can do that. We have a number of different functions for applying treatment effects. We've already seen apply HR for applying a hazard ratio, but there are equivalent functions for applying odds ratios, as well as acceleration factors and other treatment effect variables. So there's a lot of different options for modifying survival distributions and piecing them together. So just one other thing I'd like to cover. If you have multiple parametric forms that you want to switch between, that can be accomplished using indicator variables. And so let me show an example of that. So actually I need to load an example here. Okay, so let's say we have, in the survival distributions page, defined a Weibull model and an exponential model. So here we have PFS chemo Weibull, and here we have PFS chemo exponential. And we'd like to be able to easily switch between those two while looking at the results. So what we're going to do is first we're going to go back to the parameters page, and we're going to create a variable which represents the selected PFS distribution. So we've called this one PFS dist, and then the value is just Weibull in quotes here. And we're putting in quotes because we're signifying that this is a string value, a character string, rather than a variable that's being referenced. And so this variable is going to take on the value of Weibull by default. And then going back to the survival distributions page, we're going to use the if function here. We've got this variable PFS chemo, and if the PFS distribution equals Weibull, we're going to use PFS chemo Weibull, and otherwise we're going to use PFS chemo exponential. And so when we go to the ref page, here we've got an override set to use exponential, but we can change that to Weibull, recalculate it, and you'll see that the distributional form will change. And so if you want to go back and forth between multiple different distributional forms, that can be done. Ultimately, we plan on adding a sort of a user interface builder on top of these models that you build, and that'll allow you to create a drop-down for those indicator variables so that ultimately an end user, rather than a modeler, will be able to simply select from a drop-down of whatever options that you specify. But for now, we use these indicator variables. Now, actually, before we get on to help and support, I just want to mention that in addition to all the survival modeling function that we've described today, it's also possible to directly estimate Kappa-Meyers and parametric distributions of various types from IPD if you load those into a table. So you can perform estimation directly on the platform, either using the code editor or potentially just directly in the survival distributions page. And that would work by creating a table with the time to event data. And then in the survival distributions page, let me actually just load a quick example of this. So in this advanced example, we've got a table with some time to event data with multiple different treatments included. So we've got a treatment covariate. And then in the survival distributions page, we're running this estimation function, which in this case fits a mixture cure model to that data as a function of treatment, and then that model is used to directly project survival in both arms. Really, there's a lot of very complex functionality in terms of survival modeling and in terms of other functionality that can be done very simply in heRo3 that takes so much longer to do in Excel. And while it's going to be a little bit of a learning curve getting used to all the different options that are available and the time that they can save you, we believe that that learning curve is absolutely worth it. And if you, of course, you're going to have questions going through this entire process. So if you have any difficulties or any questions, the first place to look is the heRo3 guide that I mentioned, which is in the question mark item at the top of the application toolbar. You can access that from anywhere, like I said, from the toolbar. However, if you need more detailed assistance, you can contact us on the Slack chat if you're on it. If you're not, send us an email and you can ask to be put on the Slack chat. Or you can just send us an email directly at heRo3support@pai2.com. And for those that don't know, Slack is just a sort of work-oriented chat application that we use both internally on the development team as well as to maintain communication with all of our testers. Please feel to contact us also if you have any feedback that you'd like to send us. We're always looking for ways to improve the application. You know, this is still a beta test. There are features that we'd like to add in the future. There may be features that we haven't thought of yet that I think would be great, and we'd like to hear those ideas. You know, this is a platform that's going to evolve over time, and we think it's going to get better thanks to all of your suggestions. So please, if you have feedback, send it to us. And lastly, I'd just like to thank everyone here for their participation in the pilot test and open the floor to any last questions.
Jordan, like the way you have for, you know, all this functionality for survival, I was just wondering if you have some sort of stuff for cost. I mean, given that cost can be very highly skewed distributed and it can take up, it can take up any of these distributions. So do you have such similar functionality for cost, or it's like interchangeable, like, you know, just wanted to get your feedback on that.
Right, so right now, we don't have any specific functions that are built to handle cost explicitly. However, I would note, of course, that you have access to all of the sort of functions that R provides for doing, you know, any kind of necessary arithmetic. You know, for example, you can use, you know, the modulo operator to make it so that costs occur, you know, every third cycle rather than every single cycle. And I would also note that everything that I mentioned with respect to model and state time dependency can be directly incorporated into costs, as well as everything relating to lookup functionality. So, for example, if you want to explicitly sort of specify the number of doses that patients get in cycle 1, cycle 2, cycle 3, you can put that in a table and then use the lookup functionality to look up, you know, as a function of model time, the appropriate number of doses they're supposed to get, and then multiply that by some kind of unit cost. But if there are specific sort of functions that you think are sufficiently sort of generalizable and reproducible for working with cost information, we would love to hear suggestions for those, because if there's any part of this platform that we can make easier and more sort of more automated, we'd love to do that. We'd love to take the pressure off your hands to come up with those formulas and instead just offer the functionality out of the box.
Jordan, I'd just like to speak because we got a question that came in the dialogue box during your presentation, and thank you so much. You did an excellent job. About, you know, positioning, where we see heRo3, what its sweet spot will be in the near term. While we very much like HTA agencies to sort of throw open their doors and welcome submissions from heRo3, we are realistic about it, and while we think that that will eventually happen, it's certainly not going to happen within the first few or several months or perhaps even a year or two of launch. Where we do see the tremendous value for this platform is in early models. First of all, the ability to develop early models quickly, robust models without, you know, literally in hours and not days or weeks, is where the real value of this platform lies. Matter of fact, ICER, Jordan had not mentioned it, but ICER has been participating in pilot testing heRo3, and we just got an email from them a little over a week ago saying they're very pleased with it, and they were able to build 2 models that otherwise would take them days in Excel in hours with heRo3. So they are very pleased about it, and we believe they're going to continue to use it and deploy it within ICER. I would also note that another obvious place for this platform is in validation of models done in Excel. Typically right now, Excel has what I like to term as faux transparency. People claim that Excel models are transparent, but in reality they're not, because nobody ever checks the calculations in the thousands or tens of thousands of cells. Relatively few companies want to dig deeper into their pocket and build a second model to validate their first model, because that's in reality the only way that you can validate a model in Excel. heRo3 provides a very easy means of validating models in Excel. You will find, once you get up the learning curve with heRo3, that the build time for models with all of these convenience functions that Jordan has been describing is the savings in time will be substantial, and I think it will open up the door to model validation as best practice in industry.
One quick question about the heRo3. So after launching, is it going to be offered free package, or is it going to be start being charged? Good for us to know.
Yeah, sure. Very quickly. So we intend to make the package available without charge to students, academics, and to nonprofit agencies such as HTA bodies. We are so heavily in debt over this. We're all eating macaroni and cheese for dinner. So the revenue model is to license the platform on a per seat basis for principally biopharma and medical device companies. But we think, given the savings that it will generate, we'll be able to price it in a way that leaves a lot of money on the table and also is sustainable in terms of providing revenue for future development and enhancement.
The last thing, so I really think heRo3 should be expanded to the budgetary models, and instead just focused on cost-effectiveness models, and that's going to open a lot of doors to heRo3, because medical devices may heavily invest on budgetary impact models here in the United States, than the cost-effectiveness models is less. So I think that is an area that I hope heRo3 will be also start giving
we would love to have that discussion. I mean, we were in partnership with Novartis, Amgen, and Merck for the initial build, and but budgetary impact models are on our radar screen. But again, at some point, we need to make certain that there's indeed a sustainable model here. So we made the decision to go for a commercial release at this point in time with markup cohort functionality and prediction survival functionality, and if we can generate sufficient interest, then absolutely budget impact models are very much within our target, as it were.